This video is an introduction to lipids and particularly about fatty acids and how they contribute to lipids. So the big idea here is that fatty acids are the building blocks of fats. Sometimes we use the term fat synonymous with lipids, and some fats are healthier than others. So this picture is of slabs of salmon, and it shows whole fish, salmon, mackerel, trout. So we hear about how fish contain healthy fats. Well, what are those fats? Well, they tend to contain fats like omega-3 fatty acids. So what are those omega-3 fatty acids? Well, the term fatty acid comes from the fact that the chain has a carboxylic acid here at the end. So we've got a carboxylic acid to start the chain off here. And so again, this whole structure is of a fatty acid. It generally takes 3 fatty acid chains to make a fat or a triglyceride, but we'll just look at one fatty acid chain here right now. So carboxylic acid on the end. Let's note how many carbons are in this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So we count every single carbon. There's 20 carbons. And then we notice that there's some double bonds along the way. There are 1, 2, 3, 4, 5 double bonds. This would be unsaturated because of those double bonds. Wow, looks like I'm not gonna be able to spell there. Unsaturated because of the double bonds in the carbon chain. So just to review, when we said that carbon chains were fully saturated, they were filled to capacity with hydrogen atoms. Let's just say I had 2 carbons in ethane. It would be totally saturated if I filled it with the max number of hydrogens. So if I put 6 hydrogens around it. But it would be unsaturated if there were to be a double bond there, because then each carbon only has room for 2 more hydrogens. So the presence of double bonds are what we call degrees of unsaturation, where something is unsaturated if it has double bonds. So unsaturated with double bonds. Fully saturated means that you have all single bonds. So when we talk about some healthier than others, the ones that are healthier are those that contain some unsaturated fat. So our fish, for example, is fat that contains a lot of unsaturated fatty chains, or that the fat came from unsaturated fatty acids, those with double bonds. And when we hear about omegas and the omega-3 fatty acids would be from this double bond that's at the end, starting at the 3rd carbon end. So starting at carbon 1, 2, 3 from the end of the chain, there's a double bond. We look at where that first double bond starts and call it an omega-3 fatty acid. So that's what makes it a pretty healthy fat. Okay, we dove right into looking at fatty acids, but let's back up now and talk about what are lipids in general. Okay, so lipids in general are a big class of biomolecules. And these are biomolecules that either contain a fatty acid let's say fatty acids, plural, because they usually do. Or they might have a steroid nucleus. I like to call them a steroid backbone. Some people might call it a steroid nucleus, but so much of it is just made up of that steroid portion that let's call it a steroid backbone. These are generally not water soluble. So what are they going to be soluble in? Well, they're going to be soluble in oil, fat soluble. You know, they're fat or oil soluble, or soluble in nonpolar organic solvents. So let's add nonpolar, organic solvents. So think solvents like a hexane that's 6 carbons long, they could be soluble in those. And now what is this steroid backbone? Well, we see this steroid backbone in estrogen here, in cholesterol, and in testosterone. So when chemists talk about a steroid molecule, we mean any of these sex hormones that have the same backbone, so estrogen, progesterone, testosterone, and then also cholesterol. So what is that steroid backbone? Let's kind of look at what that looks like in general. In general, it has fused rings. So you'll have a 6-membered ring, a hexagon, fused side by side with another 6-membered ring, hexagon. And then on this second one, if you go to the top, the very top carbon of that second one and the second carbon, there's one fused on top of it. It's almost like it's sitting on top of it, right? Like you're starting to make a honeycomb, but instead of making 3 hexagons across, you've made one left, right, and then one up from there. And then if you go to the 2 rightmost carbons on that top hexagon, you will fuse a pentagon. Now in this steroid backbone, sometimes the first hexagon is really a benzene ring, like estrogen. That first one is a benzene ring, but it's not in cholesterol or testosterone. In cholesterol and testosterone, we see an alkene. In cholesterol in the second ring, and testosterone in the first ring. And so we can really find some functional groups here. Estrogen also has 2 alcohol functional groups. Cholesterol has 1 alcohol functional group. And notice how it has, a lot of carbon chain to it as well. Testosterone has a carbonyl C double bond O, a ketone in that very first ring, that very first hexagon. And then in the pentagon, it's got an OH coming off of it, just like estrogen has its OH coming off the top of the pentagon. So they have, really quite a bit in common. We're seeing that steroid backbone in these 3 molecules, estrogen, cholesterol, and testosterone. And so those lipids are really quite a bit different than the lipids that have fatty acid chains. So this example in the lower right is a triglyceride. And so this type triglyceride, is a type triglyceride of fatty acid chains. So there are, 3 chains on this triglyceride that came from fatty acids. So let's analyze it. Going down, it says it's CH2, CH, CH2. And then there is, each carbon is bonded to an oxygen. Each oxygen is bonded to a C double bond O. So that oxygen next to C double bond O is an ester group. So there are 3 ester linkages in the triglyceride. There's 3 of everything really in the triglyceride, but there's 3 of these ester groups. So we've got these esters. And then this is a simple triglyceride. It's not what we'd call mixed. The chains are all the same. So it's a simple triglyceride, and it says CH2, 14, CH3 for each one. So, going left to right across the triglycerides, CH2 bonded to an O, bonded to a C double bond O, there's your ester, CH2 14, and then CH3. Now, something interesting, notice how there's the carbon of the ester, then there's 14 more carbons, and then there's a carbon on the end. So there's 14 carbons plus 2 more is 16 carbons in each fatty acid. These fatty acids that occur in nature, they always have an even number of carbons, which I just think is kind of a cool fun fact, is that those fatty acids in nature have even numbers, 12, 14, 16 carbons. What about this backbone? This CH2 backbone comes from having OHs off of each of those carbons, so 3 OHs, comes from what we call a glycerol backbone. So that molecule with the 3 OHs is called glycerol, and it forms the backbone of this molecule, of this triglyceride. Okay, so lipids are this broad class of molecules. They include the triglycerides. They also include the steroid backbone molecules. So again, we had 3 steroid backbones here: estrogen, cholesterol, and testosterone. And then we also had our triglyceride of a fatty acid for an example as well. Okay, a little more introduction to these fats. We have myristic acid here. So this would be an example of just a fatty acid chain. Now, we can't consume plain old fatty acids in our diet, but they do make up the long chains of triglycerides, so we need to know about them. So we recognize a fatty acid from its C double bond O and its OH from its carboxylic acid group. And then this one is entirely saturated because it doesn't have any double bonds. And if we count the carbons, it's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 carbons. The hydrogen got cut off here. Should just say CH3. So there's our fatty acid chain. Now, if we look, here is our triglyceride. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. It's not of myristic acid. It's actually of an 18 carbon chain. These are matching 18 carbon chains. So again, a simple one. Okay, so here we have a triglyceride. How do we know we have a triglyceride? Well, we see that we have 3 long carbon chains on this vertical backbone of 3 carbons. So we see we have CH2 going down, CH going down, CH2. And off of each carbon in those 3 C's is O bonded to C, bonded to double bond O. So OC double bond O, excuse me, an ester group. So each carbon is followed by an ester, 3 esters, and then each ester is followed by 16 CH2s and then a 17th CH3, and the 18th carbon is in the ester group. Okay, so it's repeated 3 times. So, we've got these long fatty acid chains on our glycerol backbone, making this a triglyceride. So what do we need to know about fatty acids? Well, these are long chains of about 12 to 20 carbons. Like I said, they're always even numbers of carbons. They have this long carbon portion that is really hydrophobic, right? It's really water fearing. Hydrophobic, fear of water. So it's not going to be water soluble. They do also have a hydrophilic end. So the carboxylic acid end of it, that part of the fatty acid is actually hydrophilic. That part will love water. So it does have a hydrophilic end, but the hydrophobic portion is the long carbon chain that's not going to be very water soluble. So, we have part that's not water soluble, a hydrophilic end, and then this hydrophobic part as well. That's all carbon chain. So, fatty acids are these long carbon chains of even numbered 12 to 20 carbons. They have a hydrophilic end, part that loves water, that carboxylic acid end. They have long hydrophobic tails that are long carbon chains. Put 3 of them together on this glycerol backbone and you actually get a triglyceride. And so far we've been looking at the simple ones that have all the same carbon chain.